Hello everyone! Thank you for choosing this video to learn about the quantum search algorithm. Before we begin, I'd like to briefly introduce myself. My name is Andrei Yelagin. I'm a physicist. Up until 2021, I worked as a research assistant professor at the University of Chicago. In February of 2021, I left the formal academic environment in order to pursue other opportunities. But in my spare time, I keep thinking about various physics problems. My main area of expertise is in experimental particle physics. I strongly believe that advances in quantum information science can and should be applied to particle physics. This way we can answer really interesting questions about the world around us, including the questions, for example, how our universe came to be the way it is. For a while, I've been running an Instagram channel dedicated for the most part to quantum information science. Now I decided to start making YouTube videos with details that are impossible to cover in short Instagram posts. Rather randomly, I decided to start from the quantum search algorithm. This video is part 1. Here I will introduce the general concept of quantum search. I will get to the quantum circuit diagram with the Groovy iterations. However, any details about how the Groovy iterations actually work will be covered in the next video, in part 2. I should also say that this is an experimental video in the sense that there probably gonna be an improved version of it in the future based on the feedback that I hope to receive. So if you have any suggestions or comments, please write them in the comment section below. And with that, let's get started. Quantum search algorithm was first introduced by Love Groover in 1996, and the algorithm is often called the Groover's algorithm. This algorithm provides the most computational advantage over the classical search when it is applied to unstructured search problems. We will say that the search problem is unstructured when the elements of the search space have characteristics or features that cannot be used by fast search methods, such as binary search, balanced search trees, hash tables. Practically, this means that if we are tasked to find an element satisfying certain search criteria, the only way to solve this search problem classically is to apply an exhaustive search method when every element in the search space is being examined one at a time until the element satisfying the search criteria is found. Let's assume that we are dealing with an unstructured search space of the size n. We have n elements. And for simplicity, we are told that there exists exactly one solution to the search problem. That is, among the n elements, there is one element with unique features that distinguish it from all other elements. And we are tasked to find that one element, which we will call the solution to the search problem. We can assume that all elements are indexed, for example, from 0 to n minus 1. And we need to find the index of the solution. As an abstract example, let's assume that all elements are squares and the element we need to find is a circle. So let's do this. We will erase this element in the middle. We'll draw a circle and we will say that somewhere there is an exactly one solution which is unique. It's circle. We can index all elements from left to right. The left element will have index x equals 0. The next element x equal 1. Then there's going to be element x equal s. We don't know what s is. We just know that we will denote s as the solution. The last two elements will be n minus 2 and n minus 1. So to be more precise in formulating the search problem, we will assume that we can only examine the search space in such a way that during one examination, we can determine whether an element at a certain position is a circle or not. In other words, one examination of the search space reveals whether an index of an element corresponds to the solution or not. We need to mention these details for two reasons. First, to emphasize that the nature of the search problem classically requires a brute force exhaustive search. And second, there exists a way to check if a particular element is a solution or not. So this is very important for building a quantum search algorithm. We need a way to verify if solution is really a solution. When doing the exhaustive search, we may get lucky and find the search element upon examining the very first element of the search space, or we can get very unlucky and we'll have to examine the entire search space before we find the solution. On average, we need to examine the search space n over 2 times. So classically, the complexity of the search problem is of the order of n. So the number of times we need to examine the search space to solve the search problem scales linearly with the growing number of elements. Surprisingly, the quantum search algorithm has complexity which is only square root of n. So the number of times we need to examine the search space in quantum search algorithm grows only as square root of n with the growing number of elements. The computational advantage due to this square root of n factor can be significant. Let's take a look at an example. So let's assume that n is equal to the power of 34, which is roughly 17 billion. And that's how many operations we would need to do in order to find the element in the classical algorithm. So on average, we'll have to do about 8.5 billion examinations of the search space. In the quantum search algorithm, we only would need to do square root of n examinations, which is 2 to the power of 17, which is about 130,000. And this is 10 to the 5 improvement. And I'm here very carefully in calling this an improvement rather than speed up in computational time, just because the actual computation time will depend on the implementation of the algorithm at the hardware level. However, in the quantum search algorithm, we would need to examine the search space on the order of 10 to the 5 fewer times than in the classical search to find the solution among 17 billion elements. We will see in a moment that in the quantum search algorithm, the search space is represented by the combined state of the search registry qubits. Each examination of the search space is accompanied by a couple of additional transformations applied to that search registry. But in the big O notations used in computer science, the complexity of the quantum search is still square root of n. So it is still fair to say that quantum search algorithm can find solution to the search problem using on the order of square root of n fewer steps than in the classical search. Now, let's start building a concrete framework for the quantum search algorithm. So we said that we indexed all elements. We will make one more simplification, and we will say that n is equal to the power of small n. So n is equal log 2 big N. And this is just a simplified explanation. Nothing depends on these assumptions. The algorithm can easily be adjusted for n to be not exactly equal, not to be exactly power of 2, but that makes just the description easier. So now what we will do, we will convert indices in the binary representation, where the binary form is given by state of the qubits. So here's what I mean. We will have small n qubits to encode all x's, all indices in the binary form. So the very left element encoding in the binary form will be all 0. So all qubits representing the search space will be in the state of 0. And we would need n of those elements. The next element will be represented by qubits all in the state of 0, except for the very last one. Somewhere, the solution will be represented by the combination of states of qubits in 0 and 1, And just as an example, let's assume that S equals 6, then it will be represented by starting all qubits in 0 state, and then the last few qubits will be in the following form, just a binary representation of the number 6, 0, 1, 1, 0. So this is 6, and again, we would need n of those qubits. The element here with index n minus 2 will be represented by qubits in the state of 1, except for the very last one. And the very last one will be all qubits in the state of 1 in the computational basis. And again, everywhere here, we have small n number of qubits. So to go back to our original example with with the 17 billion elements, the small n equals 34. That means that we need 34 qubits in order to represent search space of 17 billion elements. So in order to really implement the quantum search algorithm, we would need slightly more than 34 qubits. We need auxiliary qubits to perform certain transformations, but the core number of qubits is still 34. Let's take a closer look at the states of the search registry. Our search registry is represented by n qubits, and the very first element in our search space will be represented by the state of the search registry, where every qubit is in the 0 state in the computational basis. So we can write that this state of the search registry corresponds to the element with index x equals 0, or sometimes we will use this notation when we just write 0 in the cat notation. And this is not to be confused with individual qubit. So what is shown here is a binary representation of number 0 using n qubits. And this qubit here is just the state of individual qubit in the computational basis. So similarly, here we will have state with all qubits in the state of 0, except for the very last one, which will be in the state of 1. And that corresponds to the element in the search space with index x equal 1. Or we will sometimes just write 1. And again, this is not to be confused with individual qubit. This is the whole state representation. Somewhere we will have combination of 0 and 1s in the search registry, which would correspond to our solution with index x equal s, which we can denote just as s in cat notation. To make it a little bit more concrete, again, let's assume that s is equal 6. In this case, we will have state of the search registry with majority of the qubits in the state of 0, and the last combination will be 0, 1, 1, 0, which is the binary representation of the number 6. So we will denote this as state corresponding to an element with x equal 6, or just 6 in the cat notation. And finally, the very last element in our search space will have all 1s in the search registry. And this will be state of the search registry corresponding to the final element with index x equal n minus 1, or just n minus 1. We will start our quantum search by placing the search registry in the state with all qubits in the state of 0. So this state of the search registry corresponds to the very first element with index x equals 0. And let's just get reminded that we have n qubits overall. So as a very first step, we will apply Hadamard gate to every qubit in the search registry. So by definition of the Hadamard gate, what we will get is superposition of state 0 plus 1 divided by square root of 2. And we will get such superposition for every qubit in the search registry. This is just the definition of the Hadamard gate applied to the state of the qubit 0. So this state of the search registry, after we applied Hadamard gate to every qubit, will be called the equal superposition state, and we will denote it as E in the cat notation. So we'll write here that this is the equal superposition state. We will see in a moment why it is called the equal superposition state. We will write the expression for the state E in an explicit form. We will have this factor 1 over square root of 2 to the power of n, and then we will have this superposition of states for each individual qubit. So let's write explicitly that there will be one more here. And then, no, this is not addition, this is multiplication. So we will have n of those brackets. Round brackets. So let's just make it explicit that we're gonna have n round brackets with 0 state and 1 state. And if you open all these square brackets and remember the fact that our small n is equal log 2n, then what we will get is factor 1 over square root of n here, and then we will have all possible combination of 0 and 1s. So the very first state here will be all zeros. Then they're gonna be 0, 0, 0, 1. Somewhere here gonna be the solution, the combination of 0 and 1s representing the solution to the search problem. And we will end with the state corresponding to the element with x equal 1. So this corresponds to index x equals 0. This is x equal 1. This is x equal s. And this is x equal n minus 1. So now we can see that if we rewrite it in the following way, we can individually write terms with state of the search registry of 0. We have this factor 1 over square root of n in front of every contribution. There will be state s, and there will be state n minus 1. So basically every possible combination of the search registry is represented equally with the same amplitude here. This is why the state E is called the equal superposition state. Now let's talk about how can we get from the equal superposition state to the state S, so we can find the solution to our search problem. So let's write the state E in the following form. We'll write it as a sum of all possible states of the search registry, X. It's sum over X from 0 to n minus 1. And we have equal amplitude for every contribution of X. This contribution is, the amplitude is 1 over square root of n. Now let's assume that we do measurement on this equal superposition state. Measurement defined as M, and let's assume we get state S. The probability of that to happen is determined by this amplitude 1 over square root of n, which need to be squared to get the amplitude, to get the probability. And this is equal 1 over n. This can be extremely small number if n is large. So if you just measure the equal superposition state, we are very unlikely to find the solution. So what we have to do, we have to find some unitary transformation from state E to some other state, which we will denote as psi S. And that state, again, will have all contributions from every index X. But this time, the amplitude for each contribution will depend on the index X. Indices run from 0 to n minus 1. And what we'd like to get to a situation where the alpha S, when X is equal S, is very close to 1. So when we measure that psi S state, we get final state S with high probability. And we'd like all other amplitudes in this psi S state to be very close to 0. The unitarity condition has to be satisfied. So summing up all possible, all amplitudes squared should be equal to 1. And just to rewrite it, what you just said, if we do measurement on the state psi S, then we get the solution to the search problem with high probability. And that probability is equal alpha S squared. And we said that this is a number which is very close to 1. So if you look at the whole procedures that we just described, what we'd like to do in the quantum search algorithm is the following. We are starting in the search registry state of 0, where every qubit is in the 0 state. Then we apply Hadamard gate to every individual qubit, and we get to the equal superposition state. Then we'd like to do some unitary transformation. So E transition to the state of psi S. Then we do measurement. And as a result of that measurement, with very high probability, we get state S. So what's drawn in this box is a unitary transformation. This is just some kind of amplitude manipulation that would lead us from state E to state psi S, where amplitudes alphas have this property that alpha S is equal or very close to 1, and alpha X, where X is not equal to S, are very close to 0. So let's write here amplitude manipulation. This is jargon, but nevertheless, it's an important concept. To be more precise, this is unitary transformation. And this unitary transformation changes amplitudes of the equal superposition state in a way that we are very likely to measure the state S. Now let's summarize what we described so far by drawing a circuit diagram for the quantum search algorithm. We said that we start our search registry in the state of 0. So every qubit starts at the state of 0. And then we apply Hadamard gate to every qubit. Let's draw that. So here we have search registry state at the state of 0. After applying this Hadamard gate to every qubit, we get to the state E, the equal superposition state. Now we need to do those manipulations to the amplitudes of the equal superposition state. And we do that by applying several unitary transformations of a special kind. Those transformations called Gruber's iterations. So this is one Gruber iteration. Then we will apply the next one. Denote them G due to Gruber, the person who invented this search algorithm. And then we will apply the last one, last Gruber iteration. Again, we denoted G. And these Gruber iterations represent the amplitude manipulations that we talked about before. And after we've done with those amplitude manipulations, we end up in a state psi S, which if we measure, we have very high probability of getting the state S. So let's do the following. So we draw here that we get to the state psi S over here, and then we do measurement. Let's denote measurements by the double wire. And that results in the state S, that once we look at the search registry after the final measurement, we'll know the S just by its binary encoding of the number S. We have to do Gruber iteration square root of n times. And those Gruber iteration is what involves examining the search space that we talked about at the very beginning. One detail here that in order to implement these Gruber iterations, we have to introduce ancillary qubit. Details of how it is done, we'll talk in the following videos. But for now, just for completeness, I'd like to draw a line here and call it ancillary qubit. This qubit does not interact, or qubits. So depending on the implementation, it is a one or several qubits. These ancillary qubits do not interact with the search registry. So in that sense, they are independent entities. They are needed purely for implementation of these Gruber iterations, and they do not affect directly search registry. So this is a complete circuit diagram for the quantum search algorithm. The core, of course, is in the Gruber iteration. So this diagram just gives you the overall concept of how the quantum search algorithm works. In the next videos, we will discuss the details of Gruber iteration, how they work, why exactly we have to apply them square root of n times. We will discuss what happens if we measure state psi S and while small probability, but it is non-zero, that we will not get the state S and we will not know the solution. So what we do that in that case, but for now, I hope this video gives you the overall concept how the quantum search algorithm works. Thank you for watching this video on the quantum search algorithm. I hope you found it useful. If you did, please make sure to share it with other people who you think might benefit from watching it. In the next video, we will talk about the Groover iterations in great details. So I'm really looking forward to see you in that next video.